Hi, I am presenting Reason Match, eliciting complex spatial reasoning in MLLMs through wide baseline matching. The high-level question is whether a multimodal language model can identify the same physical region when the viewpoint changes dramatically. This is a basic capability for physical world intelligence. A robot, an embodied agent, or a visual assistant cannot rely only on object names or captions. It must understand how the same scene element appears from different views, under occlusion, partial overlap, repeated structures, and local distractors. We study this through wide baseline matching. Given two views of the same scene or object, the model receives marked regions and must output the cross-view correspondence. Some regions match one-to-one, some are visible only in one view, and some are confused by target-side distractors. This task forces the model to combine geometry, semantics, fine-grained perception, and contextual reasoning. Our first contribution is Reason Match Bench. It contains 2,810 balanced region pair questions across indoor, outdoor, and object-centric scenes. The benchmark is stratified by viewpoint displacement and matching granularity, so it covers not only easy overlap cases but also hard wide baseline settings. This makes it a useful testbed for evaluating whether MLLMs can reason about physical correspondence rather than only answer coarse VQA-style questions. The benchmark reveals that current models still struggle. Strong general-purpose systems can describe local content, but often fail to bind those observations into a globally consistent correspondence. On the full benchmark, GPT-5 Mini reaches 57.9 F1 and Gemini 2.5 Pro reaches 42.8 F1. The base Qwen 3 VL8B model reaches only 27.5 F1. On a difficult human study subset, humans reach 84.0 F1, while our trained DCRL model reaches 52.0 F1, so there is still a large human gap. To improve this ability, we build a scalable data generation pipeline from video 3D data. The key observation is that RGBD videos and structure from motion reconstructions already contain many real cross-view observations. We can automatically harvest wide baseline pairs, project or verify shared scene elements, and construct diverse matching questions with reliable correspondence labels. This gives us supervision that is both scalable and verifiable, without manually writing chain-of-thought annotations. Our training method is Dynamic Correspondence Reinforcement Learning, or DCRL. Instead of imitating a fixed explanation, DCRL rewards the model according to the correctness of its final matching output. The reward is holistic. It evaluates all query regions, including unmatched or out-of-view points, so the model must decide both what matches and what should be mapped to no correspondence. DCRL also uses a two-level curriculum. At the image level, viewpoint progression starts from higher overlap pairs and gradually moves toward more extreme viewpoint changes. At the point level, the correspondence curriculum changes the matching structure, moving from unambiguous one-to-one matching to distractors, partial matching, and more challenging spatial distributions. The goal is to let the model build stable intermediate competence before training on the hardest cases. The main result is that this training substantially improves Reason Match Bench. DCRL raises Qwen 3 VL8B from 27.5 to 70.5 F1, outperforming the stronger closed-source baselines shown here. The gains are visible across indoor, outdoor, and object-centric scenarios. This suggests that targeted training on verifiable wide baseline correspondence can be more effective than simply relying on larger general-purpose models. We also test whether the improvement transfers beyond Reason Match. DCRL improves omnispatial, MindCube, and SAT Real, while maintaining general visual understanding performance. This is important because those benchmarks do not share the exact same format as Reason Match. The transfer suggests that the model is learning a broader spatial reasoning capability, not only memorizing a benchmark interface. The comparison with supervised fine-tuning helps explain why reinforcement learning is useful here. SFT improves in-domain Reason Match performance, but transfers less reliably and can degrade performance on some spatial benchmarks. In contrast, DCRL improves Reason Match and transfers more consistently. This supports the idea that outcome-verifiable reinforcement learning can encourage more robust spatial strategies than teacher-forced imitation. Finally, the curriculum ablation shows that the training schedule matters. Uniform sampling is already stronger than training only on easy or only on hard samples, but dynamic curriculum achieves the best result. This indicates that progressive difficulty adjustment across viewpoint divergence and correspondence complexity is beneficial for learning wide baseline spatial reasoning. In summary, ReasonMatch frames cross-view region correspondence as a scalable and verifiable way to evaluate and train spatial reasoning in MLLMs. ReasonMatch Bench exposes clear limitations in current models. DCRL shows that curriculum reinforcement learning with exact correspondence rewards can substantially improve this capability and transfer to related spatial tasks. At the same time, the remaining human gap shows that robust physical world spatial reasoning is still far from solved. Thank you.